In this video, I'm going to be talking about the second law of thermodynamics, and I'm not going to be really getting into any math or derivations in this video because I feel like in order to, before getting into the math related to the second law, I feel like it's really helpful to have kind of an understanding of how the law, or why the law developed, and then look at some of the statements related to the second law of thermodynamics. So unfortunately, for the second law, the first law is just an energy balance. So the first law, we can just derive an equation. So we can just do it. So for the first law, we just had our system, and we just know that we had a certain amount of energy in, and then we had some energy out. So this would just be a really general energy balance. And then there was a change of energy in the system depending on what was going in and what was going out. So with the first law, it makes sense to just do a mathematical derivation because it's really intuitive what's going on just from the math. The second law isn't quite so intuitive, and I feel like if you just start seeing the math right away, it gets really confusing. So I'm going to try and show some examples of what led to the need for the second law, and then in later videos we're going to get into the math related to the second law. So first of all, why do we even have the second law? Like, why do we need the second law? I mean, we've been using the first law so far to solve problems, and it seems like things have been going pretty well. Like, we've been getting answers for things, and it doesn't seem like it's been a problem. But basically, the reason why we have the second law is because of the first law. So the second law was developed because of the first law. So developed because of the first law. And basically the reason why is because the first law says that energy is conserved. So if we say the first law says energy is conserved, but the problem is it doesn't put any restrictions on how that happens. So there's no, I'm going to put no restrictions. So what do I mean by restrictions? Well, let's look at some examples. So let's say that we have a container of gas, and I'm just going to call it gas. And let's say that we have a mixer in here, so we're adding some work to the gas. So we know from the first law that this work is going to heat up the gas. So basically we're going to input work that's going to heat up the gas, so we're going to increase the internal energy of the gas. Well, okay, so now that we've heated up that gas, can we take that heat from the gas and run the mixer? Like, so we've run this mixer for a while, we've heated up the gas, so now we have heated gas, and let's say that we have this mixer, like let's say that this is hooked up to like a generator or something. Can we take the heat from this gas and use it to run that mixer and, say, generate electricity or something else? Well, we know that we can't. We can't do that, so we can't take the heat from the gas and run the mixer. But the problem is that the first law doesn't put any restrictions on that. So if we look at the first law, we just have Q minus W is equal to delta U. This is assuming our potential and kinetic energies are zero. So the first law doesn't put any restrictions on this. So according to the first law, it looks like we can convert the work into heat, or we could convert the heat into work, like either way. So the first law isn't putting any restriction on that process, even though we know it can't happen. Let's look at another example. Let's say that we have a stretch spring. So we have a spring that's been stretched out. Like, let's say it's connected to something that we're pulling on the spring. And then let's say that we let the stretch spring compress. So now the spring is going to compress. Well, so we know that there's going to be energy lost as heat from the spring. So when the spring compresses, we're going to have some energy lost as heat. Well, okay, so can we then take that heat? So let's say that we have the spring, can we take this heat, add it to the spring, and use it to stretch the spring back to its original size? Well, we know that we can't. Like, we can't take this heat and use it to re-stretch the spring. We need some kind of work input to re-stretch the spring. And so we can't take that heat and use it to re-stretch the spring. So basically the heat is still going to be in the atmosphere somewhere, and it's basically just kind of lost. So like if we look at our energy balance again, we have Q minus W is equal to delta U. So if we look at the first law, I don't see any restriction in there that says we can't take that heat and use it to re-stretch the spring. I mean, it looks like it could work either way. And let's look at one last example. So we all know that heat transfer occurs from hot to cold. So let's say we have two containers next to each other. One of them's hot, one of them's cold. We know that heat is going to transfer from the hot side to the cold side. And we know that this heat transfer is going to occur until these are the same temperature. So I'm just going to say after some time, these are both the same temperature. So let's just say that, I'm just going to say same temp for both. So we know that the heat's going to transfer from the hot to the cold side until they're the same temperature. And after they're the same temperature, that transfer is going to stop. Can we say that, like, can heat be transferred from the cold side to the hot side? So we know that heat isn't going to transfer from the cold side to the hot side. And we also know that, like, if we have this container where they're the same temperature, we aren't going to have, like, these aren't going to, like, we're not going to have heat transferring from one side to the other until one side becomes hot and one side becomes cold. Like, that process isn't going to naturally occur. So now let's look at, let's take this and expand on it a little bit. So we know that we can have, so we know that if we have a hot side and a cold side, or a hot body and a cold body, we know that heat is going to transfer from the hot body to the cold body. Well, what if we then put something between these two bodies? So now we have something in here, and I'm not going to specify what's in there yet, but let's just say that this is a black box. And so let's say that as the heat's transferring from the hot side to the cold side, we're generating work somehow. So in order to generate this work, we need to have this heat transfer from the hot side to the cold side. So it needs to go from the hot side to the cold side. In other words, we need to, in order to produce this work, the heat needs to be rejected to a cold source. And if you don't believe me that we need this heat rejection in order to generate this work, just try draining all of the radiator fluid out of your car and see what happens. So if we just look at the first law for this, there's nothing in the first law that says we need this heat rejection. So according to the first law, we could potentially just produce work from the hot side. So we could just take this Q, so we have this Q here, we could just take that heat and produce work according to the first law. So there's no restriction in the first law that says we need this heat rejection to the sink. So basically what I'm getting at is just because the first law says something can happen, it doesn't mean that it will. I'm going to write that down. So just because the first law says something can happen, that doesn't mean that it will. And so basically what the second law does, so the second law puts a restriction on the process. So the second law puts a restriction on the process. And so now let's get into, like, if you look up the second law, you'll often see a few different things. So first of all, you'll see that it's also called the law of dissipation, the law of degradation of energy, and last but not least, the law of increase of entropy. So probably the description I like the best is that it's the law of dissipation. And the reason why is because we've already seen from all of these processes up here, well, specifically this this process where we have heat that's going from the hot side to the cold side, and it's not going in reverse, we know that basically if we leave a system by itself, its energy is going to dissipate. So basically it's going to move towards a state of equilibrium. So let's say that we have a can of soda and it's at 5 degrees Celsius and we put it on the counter, and let's say the room is 20 degrees Celsius. We know that the soda is eventually going to heat up until it reaches the temperature of the room. So basically heat is going to be transferred from the room into the soda, and the soda is going to heat up until it's at equilibrium. So it's going to move towards a state of equilibrium. So basically a system left to itself dissipates its energy, and basically what that means is that it's moving towards a state of equilibrium. So moving toward equilibrium. So basically what's happening is the energy is spreading out spreading out or dissipating until it reaches equilibrium. So at equilibrium, these are going to be the same temperature. And I'm assuming the room is a reservoir, so the temperature of a reservoir isn't going to really change when it loses heat, because the room is so big compared to the soda. So eventually the soda is going to be at 20 degrees Celsius as well, and this is going to then be in equilibrium. So another example of this is, let's say that we have a container of water and we put some food coloring in here. We know that the food coloring is going to diffuse through the water until it's basically dilute. So initially the food coloring is going to be really concentrated where it's dumped in, but it's eventually going to move through the water until it's dilute. So then we're going to have food coloring equally distributed throughout the water, whereas initially it was all right here. And that's going to happen naturally on its own. So basically the system is going to move towards equilibrium. So if we consider these two systems, so I'm going to consider the soda and the water. So let's say that we have the water with the food coloring. So here's all the food coloring. And let's say that we have this soda that's at 20 degrees Celsius, so it's at the same temperature as the room. So we know that this soda isn't going to just spontaneously start losing heat and return to the 5 degrees on its own. We also know that this food coloring isn't going to spontaneously all move to one side of the container and so sort of separate itself out. Like, we know that's not going to happen. But we can cause the soda to return to its original temperature if we supply some sort of external work. And we know that because we have refrigeration. So let's say that we have the soda, and let's say that we put the soda in a fridge. So here's our fridge, here's the soda, and the fridge is plugged in, so it's getting some electrical work. So we're inputting electrical work, and what's going to happen is this refrigeration cycle is going to take heat from the soda and move it out into the room. So basically what's going on is we're running this cycle in reverse. So we still have our cold side and our hot side. Now the cold side is the fridge, or the inside of the fridge, and the hot side is the room, and here's our fridge. And so what we're going to do is remove heat from the fridge and move it out into the room. But this requires work input for that to happen. And so the work input in this case is electricity. So the fridge takes heat from the food, rejects it to the room, and this requires work input. So basically what this means is that no system is going to move in the opposite direction away from the equilibrium without some sort of external work. So for instance, if we have the soda and let's say that it started out, so it's at 5 degrees, it's in the room, so it's not in the fridge anymore, it's in the room. We know that heat's going to spontaneously transfer from the room to the soda, and the temperature of the soda is going to increase until it reaches equilibrium. So this is only going to happen in one direction, basically the heat transferring from the room to the soda, unless some sort of external work is put into it, like it's put into the fridge. And we know that this heat isn't going to start transferring the opposite direction just spontaneously. And we also know, like if I go back up here to this spring, so we know that we can't take the, well, so let's go back to this mixer, so we had this mixer that was adding work to this gas and heating it up. We know that we can't take that heat from the gas and use it to run the mixer. The same thing with this spring. When the spring compresses, it's going to release heat to the room. We know that we can't take that heat and use it to restretch the spring. We need work input to do that. So the same thing with this fridge. If we go back down to this fridge, we can't take the heat. So this fridge is going to remove heat from the soda, put it in the room, and it's using electrical work to do that. We can't take that heat and use it to do work. It's basically lost to the environment. And so just based on these few observations that I've talked about, the second law is really based on observations. The second law is based on observations. This one is what's known as the Kelvin-Planck statement. And this statement basically says that no process is possible. So no process is possible whose sole pursuit is absorption of heat from one reservoir and conversion of this heat to work. So basically what this is saying is that we can't convert heat to work without a heat sink. So in other words, if we go back to this that I showed you earlier, where we had the heat being transferred from the hot side to the cold side, and we had some black box in here, and we're using that to generate work. We can't run this like this. Like, we can't just have the heat and convert this directly to work without having some sort of sink. So this isn't going to work. So basically the Kelvin-Planck statement puts a restriction on what's known as heat engines. So we're going to talk about this later, but this is basically a heat engine. So we're converting heat into work with a heat engine. And we need the heat sink in order for that process to work. And then another statement for the second law is what's known as the Clausius statement. And this one says that no process is possible that results solely in the transfer of heat from a cold to a hot reservoir. So this basically means that if we want to transfer heat from a cold to a hot reservoir, so let's say that we have our cold reservoir and our hot reservoir. So if we want to transfer heat from the cold reservoir to the hot reservoir, this is going to require work input. So we can't transfer the heat from the from the cold to the hot reservoir without some sort of work input. So basically this statement puts a restriction on refrigeration cycles. So this puts a restriction on refrigeration cycles. What we want to do is to quantify this restriction somehow, is to see if the process violates the second law. So we want to quantify the second law. And so what we want to do is we want to quantify it to see if the process violates the second law. So in other words, if we have a heat engine and we're trying to run it without having a heat sink, that's obviously going to violate the second law, even though it'll be fine for the first law. And with the Clausius statement, if we're trying to run a refrigeration cycle without inputting some sort of work, that's going to violate the second law, even though the first law says that that should be just fine. So the way I'm going to approach this is first, and this is going to be in future videos, but I'm first going to talk about cycles. And so we're going to quantify the second law with cycles, so specifically the Carnot heat engine cycle and refrigeration cycle. And then after we talk about cycles, we'll talk about processes. And processes is where we can define the term entropy. So we're going to get into that later. But basically, just to summarize, we have the second law because the first law doesn't put any sort of restriction on the type of process that we can have, and we know from observation that some processes just don't happen. And so what we want to do is, now that we have the second law, which is basically saying that some processes can't happen, we want to quantify that second law somehow so we can just do a calculation. So say we're presented with a certain process, we can just do a calculation and figure out if that process is actually possible or not.